Quotient rule. So I told you it was f prime g minus g prime f all over g squared. Right, g squared's on the bottom. That's not the way that they have it written. They have it gf prime, but is gf prime the same thing as f prime g? Like 2 times 3 is the same thing as 3 times 2. It doesn't matter how you order them, okay? So I would do the f first. F prime g minus g prime f all over g squared, okay? On number 1, what is f? The top. G is always the bottom. Okay, that's how you decide. F is the top, G is the bottom, then you just go. These you cannot use the power rule on. Like even if you wanted to, you couldn't FOIL like what we could have done above. These ones you have to use the quotient rule on. There's no ifs, ands, or buts about it. Okay? So we want f prime on the top. F prime g minus g prime f. I always write those down. And g squared on the bottom. I would just kind of write my skeleton of like what I have and what I need, and then I know I'm not forgetting pieces. So f prime is what I want first. So I want the derivative of the top, basically. What's the derivative of that top going to be? 5. Okay, on the bottom, I just rewrite the g, x squared plus 1. That's my f prime g. So f prime g, if you want to cross them off as you go, that's fine. Cross off f prime, cross off g, we are done with those. Okay, minus g prime. What is that going to be? Just 2x, yep. Okay, g prime is done. And f is 5x minus 2. Okay, on the bottom, x squared plus 1 squared, because it's g squared. So the entire g and then squared. Okay, that makes sense? Okay, let's go ahead and simplify this just a little bit. Really, the top isn't too bad. If you distribute the 5 through, I don't know, 5x squared plus 5. Okay, now be careful with that minus, because think of this as like minus 2x, right? You have to distribute the negative with the 2x when you go to the 5x and the 2. So negative 2x times 5 will be negative 10x squared, okay, plus 4x. Does that make sense? So if it helps you to think of it this way, like do plus negative, right? That negative is going with the 2x, right? Okay, don't forget to do that, because that's where you get stuck. Okay, all over, I'm going to leave the bottom. I'm not going to FOIL the bottom out. Don't FOIL the bottom out. Let's simplify the top. Last thing. Negative 5x squared plus 4x plus 5. All over. Still leave that. There you go. That's my derivative. Okay. Now, this is still fair game. What they're probably going to have us do next is they'll say, find the derivative, but at this point, right? At a certain point. So like at the point, I don't know, negative 1, 1. So as soon as you get the derivative, then what do you do? Plug in like negative 1 for x, right? And then that will give you the actual number for the slope of the tangent line, right? Okay, find an equation of the tangent line. We need the whole equation. What's an equation of a tangent line look like? What's the equation of a line? Y equals mx plus b. Okay? So we need the whole darn thing. We're going to find what first? M. We're going to find m first. Okay? And to find m, we take the derivative and plug in negative 1. Negative 1 because it comes from there. Okay, so we take the derivative of that top thing, and then we're going to plug in negative 1. Yeah. Okay, now, I am going to rewrite this thing. This is a quotient, right? So we have to use the quotient rule. Okay, we're not dealing with product, we're dealing with quotient. So quotient rule for this guy, but I don't like the way that top is written. 3 minus 1 over x. Okay, how can I make 1 over x be nice? Kind of. Yeah, it would be like the same as 3 minus 1 over x, but I want to get him so that he's ready to take the derivative already. Yeah, so I'm going to put like the x to the top. Even though he's in the top, I want him in the top of the top. Does that make sense? Like he's in the top part, but I want him in the top of the top. So I'm going to rewrite this as 3 minus x to the negative 1 power. Does that make sense? 1 over x is x to the negative 1 power. Yeah? Yeah? So that's what my f is going to be. This is f, and this is g. Okay, now I need my derivative. Okay, so f prime g minus g prime f all over, I'll leave some room, all over g squared. Okay, so the top, f prime. So I want the derivative of that 3 minus x to the negative 1 power. What does that make? X to the negative 2. Did I do that right? The 3 goes away, the negative comes down in front, but it's already negative, so it turns it positive. X to the negative 2 power. Okay, just leave them like that. We'll fix them maybe here in a minute. Okay, so x to the negative 2 and g. G is x plus 5. That's what g is. Minus, what's g prime going to be? Oh, nice. 1 and 3 minus x to the negative 1 power. That's what f is. Okay, all over g squared, x plus 5 squared. Okay, now, the beautiful, beautiful thing is, if you are plugging a number in, you don't have to simplify at all, because you're going to plug a number in, you're going to get a number out, right? It doesn't matter how ugly it was to start with. But I am going to change that x to the negative 2 to be x to the positive 2. Can I do that? So this guy right here, if I think about this thing, x plus 5 over x squared is what he looks like. Does that make sense? X to the negative 2 and x plus 5. If I move him to the bottom, he'll be still on the top, but he'll be the bottom of the top. Does that make sense at all? He'll be the bottom of the top. Okay? Minus 3, if I distribute the 1 through, really. And then minus 1 over x. Right? If I change him back. And I didn't do something right. What did I not do right? It should be plus 1 over x, right? Because this negative goes with the 1, right? So plus 1 over x. So don't let that get you. That's going to be where you get stuck. With the quotient rule, make sure you distribute that negative to the last piece. Okay? All over x plus 5 squared. Okay? Now, because we're plugging negative 1 in, this is going to come out really nicely, I think. Or should, anyway. Should, anyway. Okay? So even though this was really ugly to start with, we should get we might get a fraction, but we should get like a decent number-ish, maybe. Okay, so negative 1 squared, negative 1, blah, blah, blah. Okay, so negative 1 plus 5 is 4. Negative 1 squared is just 1. So this is 4 minus 3 minus 1 on the top, yeah? I don't know, maybe. On the bottom, negative 1 plus 3 is 2. 2 squared is 4, so I get, oh man, 0 over 4. How does that work? What? What? That is nuts. Right? Did I do that right? Is that what you guys got? Yeah? 0? So my slope is 0. Oh. All right, so now what? Yeah, it's a straight line. Find b. So I really have, like, if it helps you think of it this way, y equals 0x plus b. And then how do I find b? You have your point, negative 1, 1, right? Plug that in, solve for b. And I have something like b is 1. So y equals 0x plus 1, or just y equals 1. That's my equation of my tangent line. Y equals 1. Okay, y equals 1 is a horizontal line that goes like this. So I probably have like a humpy thing going on there. Right? So what's probably happening is, like, my graph is probably doing, let's see, negative 1, 1 right here. He probably is doing, I don't know, something maybe like this. Yeah, and that's the equation of my tangent line. Does that make sense? This tangent line right here is where that hump is. So y equals 1 would be that line. Does that make sense? Yeah? So You don't have to graph it or anything like that, but just so you know what we're finding, that's what he is. Okay. All right. Here we go. So this is kind of what we've been talking about before, where we do like first derivative and second derivative and third derivative and fourth derivative, etc. Right? Okay. First derivative they label as y prime, or they'll say f prime of x. Right? That's how you note the first derivative. Okay. That's the notation that you use. F of x is the original, or s of t, or whatever. Second derivative, they use two prime things. So y double prime is what I'll call him. Or f double prime x, that's the second derivative. Okay? If you're taking a third derivative, which we will like just a couple times in this class, it's triple prime. Or f triple prime of x. Triple prime. Okay, that's the third derivative. But anything after that, because I don't want to like sit and tally forever, right? Okay. Is y, and it looks like to the fourth power, but the fourth power is in parentheses, so you know it's not the fourth power, it's the fourth derivative, right? So it's 4, or f, 4 in parentheses x. That's how you do the fourth derivative or the fifth derivative the same way. Anything after 3, you label with a number, okay? We will usually only do first or second derivative. We won't do too many thirds or fourths. They will have you do them. Like just a couple times throughout this class, but usually it's only first and second, okay? Because the first one, so this is first derivative, has to do with velocity, and second derivative has to do with acceleration, okay? The original function is just the position function or the height function. Like we've had before, where you're dropping a ball from a certain height, and this is the equation of the height. That's the original function. You take the first derivative of that, you can figure out the velocity at any point in time. You take the second derivative, you can find the acceleration of the ball at any point in time along that curve. Okay? So there's that. All right, that's what the first, second derivative look like. We won't do third or fourth very often, but you might see it. Okay, let's go to the back side. One question. Woohoo! Finding the acceleration due to gravity. What? Who was that? What was that?
No, there was no one up there.
I think it was A. Right? Wow. You're magical. Right? Alright, so because the moon has no atmosphere, a falling object in the moon encounters no air resistance. Okay. I don't know if you guys have ever watched like videos or whatever, but like how they wash their hair in space. Have you seen that before?
Yes.
They have to like squirt it out of a pouch, and then like it's weird. Or like they can't have any open drinks or anything. They have to have like a squeeze bottle. It's just weird how that operates. Like think about like if you were pee, they have to have like a vacuum that like sucks the pee out of you. Otherwise, it would just be pee floating around all over. Like that's disgusting. But you have to like think about that, right? Okay. They have like special bicycles that you have to ride when you're up in space. Otherwise, by the time you come back down to Earth, your like muscles are so fatigued that like you can't even stand up when you get down to Earth because it like feels so heavy, you know? Okay, whatever. I think that's interesting. So no air resistance. I know. Sure worked for NASA, right? That'd be kind of cool. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon because there's no air resistance. A hammer and like a pencil should fall the same on Earth, even though one's heavier than the other. But a feather and a hammer won't fall the same amount because a feather will do this, right? Because there's air resistance. But on the moon, it will fall the same way. Okay. There is a gravitational pull on the moon. Like it will eventually like fall, but it will be very slowly. Okay. The position function for each of these following objects is given by this. Okay. So this is the moon. This is the position. Okay. So if I'm dropping an object or whatever from a height of 2, that's kind of what this equation is doing. The acceleration due to gravity is 0.81. What's our acceleration due to gravity? 16 if this is in feet. Is this in feet? Height is in meters. So what's ours? 9.8. Okay, so I'm going to put that down here because the Earth's gravitational force is 9.8 meters per second squared. Okay, 9.8 meters per second squared. So we have to figure out what the gravitational pull is for the moon. Okay, And this is acceleration due to gravity. What is the ratio of Earth's gravitational force to the moon? So we want the acceleration due to gravity. Acceleration. Where does it say? Does it say acceleration anywhere? Oh, acceleration due to gravity, right here. So, if this gives me the position, what do I need to do to find acceleration? The second derivative. The first derivative will get me velocity of that object, whatever we're falling. Okay, so let's do the first derivative. What will that look like? I don't know, 1.62. See if that's right. T. Okay, what happens to the 2 on the end? Drops off, okay? And then if I do it again, the second derivative, that gives me the acceleration. Okay, so again, if I do that again, the derivative of negative 1.62t is just negative 1.62, right? The t will drop off the end, right? Because the 1 comes down in front, that type of thing, okay? So the acceleration on the moon is negative 1.62. Really, I should put a negative in front of the 9.8 because it's negative 9.8 meters per second squared, okay? On the moon, it's negative 1.62 meters per second squared, okay? So they want to know how many times our gravitational pull is than the moon's, okay? So I'm just going to divide those two. 9.8 divided by 1.62. So our force is how many times stronger than theirs? 6 times, 6.0 something, right? Times the force of our gravity is 6 times more than that on the moon. Does that make sense? Okay. So that's why you feel so funny if you go to the moon or you come home from the moon. It's because you're used to a gravitational pull that's 6 times larger than what you're actually experiencing on the moon. Okay. You feel that every day? We were talking this morning. Who was it saying? About Marcus. I was like, Marcus, do you know what gravity is? Like, he was saying something, and I'm like, oh, because I was talking about how you're shorter in the evening than you are in the morning, right? You guys know that, right? Because like during the day, gravity pulls on you, and so your joints like get more compressed, like your vertebrae going down, they get more compressed. So you're like you could be up to like a half an inch shorter in the evening than you are in the morning. Because in the morning, yeah, right. That's why you make your doctor's appointments in the morning. So like when you're laying in bed, you like stretch out and stuff. Well, when you stretch, your joints elongate, so you're taller, right? And I was saying the same thing about like weight. Okay, so I had somebody explain weight to me as like you're standing on a scale, somebody's weighing you. Your weight is a measurement of the gravitational pull upon your body at that instant. Does that make sense? Isn't that a weird way to describe your weight? It's a measurement of how gravity is pulling upon you, right? It's like going toward the scale. I don't know. I thought that was interesting.
Free room giveaway at Northwest.
So there's that. Oh shoot, I'm still recording. Hi, Madison. Bye, Madison.